Welcome to the deep dive. Today we're digging into ADAM. It's a gradient-based optimization algorithm, first order, and really key for stochastic objective functions. You see it everywhere in machine learning.
It really is. Think of it as a way to help models learn better when the path isn't totally clear.
Right. And the problem it's solving? Oh, well, it's about efficiency, isn't it? Especially when you're optimizing in these really complex, kind of noisy situations.
Uh-huh. The old ways, things using second derivatives, they just don't scale well. Think high-dimensional parameter spaces or noisy functions, maybe from something like dropout regularization. Adam tackles that.
Okay, so the core idea,
Yep.
it's adaptive, right? Our source material says it computes individual adaptive learning rates, uses estimates of lower order moments of the gradients.
Yeah, that's where the name comes from. Adaptive moment estimation. It's looking at the first moment, the mean, and the second moment, the uncentered variance of the gradients.
Like giving each control knob its own speed setting based on how it's been behaving.
That's a good way to put it. And the advantages are pretty significant, according to the research. It's straightforward to implement, which is always a plus.
Uh-huh.
Computationally efficient, too, doesn't demand a lot of memory. And crucially, it's invariant to diagonal rescaling of the gradients.
That rescaling point seems important. Means it doesn't get confused if some gradients are naturally much larger than others.
Basically, yes. It normalizes things in a sense.
And the sources really emphasize its suitability for, well, the big stuff. Large data sets, large parameter spaces.
Which is exactly what modern machine learning deals with. Plus, it's good for non-stationary objectives situations where the goalposts kind of shift during training.
And noisy or sparse gradients, too.
Yeah, handles those well. The paper also mentions the hyperparameters have pretty intuitive interpretations, and the defaults usually work quite well.
Those defaults. 80 at 0.011,
Right.
80 at 0.9, BD2 at 0.999, and 8 like 10.8. They suggest you often don't need much tuning.
Often, yeah. It saves a lot of guesswork. And if you look at where it came from, it cleverly combines some advantages of earlier algorithm.
Like AdaGrad, for the sparse gradients.
Right. It gets that benefit. But it also borrows from RMS prop, which helps it work well in online settings or with those non-stationary objectives we mentioned.
So it's kind of a hybrid, taking good bits from its predecessors.
In a way, yes. It also offers approximately bounded step sizes, controlled mainly by that alpha parameter.
And it naturally does a kind of step size annealing, like it adjusts the learning rate downwards over time automatically.
It tends to, yeah, as part of how the moments are calculated and used in the update, it's built into the mechanism.
Okay. So our mission here is really to get under the hood, understand these core mechanics and the benefits that the research paper lays out.
That's the plan. Understand how it works and why it's effective.
All right, so wrapping up our discussion, let's quickly recap ADAM's main features. Those adaptive learning rates are central, based on the first and second moment estimates.
And don't forget the bias correction. That's important early on when the moment estimates might be a bit skewed because you haven't seen much data yet.
Good point. Keeps things stable at the start. And as we said, it's invariance to the scale of the gradients.
Then there's the empirical evidence. The paper shows ADAM performing really well across different models. Logistic regression, sure, but also multi-layer neural networks, even convnets.
On standard data sets too, right? MNLAST, IMDb, SAFAR 10. It seems broadly applicable.
Definitely. The results suggest it works well, and it shows strength with sparse features, much like AdaGrad.
Which can mean faster convergence sometimes, compared to other methods, especially in those sparse scenarios.
Yes, the paper often highlights its convergence speed compared to other stochastic optimization techniques in various tests.
The research also touched on a variant, AdaMax.
Ah, yes, AdaMax. It's based on the infinity norm, the L infinity norm, instead of the L2 norm used for the second moment estimate in standard ADAM.
What does that change?
It leads to a different, sometimes simpler, update rule for scaling the gradients. The paper gives this recursive formula, UT max BT1 GET. It provides a different kind of bound on the parameter updates.
Interesting, a slight variation on the theme.
A potentially useful one in some cases.
So maybe a final thought for everyone listening. Think about this core concept. Adapting your approach based on past performance, considering both the momentum, like the first moment, and the variance or spread, like the second moment. How could that idea, that adaptive strategy, be useful beyond just optimizing machine learning models, maybe in other complex problem-solving areas?
It's a powerful principle, adapting based on history and uncertainty. Definitely food for thought.